what we want to look at today, since we've been learning so much about intermolecular forces, how we measure the effects of intermolecular forces is on the physical effects that they manifest. And they manifest themselves in a couple different ways. One of the easiest to measure is boiling points and melting points of substances, because the forces that connect molecules together to make solids and liquids are the intermolecular forces. They're not determined by the bond forces in between atoms that hold molecules together. They're the molecules interacting with each other that determine whether or not they're going to be gases or liquids or solids at different temperatures. We'll learn about some other ones as well. We'll learn about viscosity, and we'll learn about capillary action and surface tension and stuff like that that's also involved with these. But the most easy to understand and sort of easy to measure are boiling points and melting points, because we can measure those very, very accurately. So we're going to look at the first site we're going to look at is just looking at the polarity of molecules. And it's sort of like, it'll be a good review for some of the lessons we've done before about, molecular shape, dipoles, bond dipoles, and how how you put together bond dipoles in a particular three-dimensional shape, whether they add together, do they subtract from each other, how do they affect each other through the shape to create an overall molecular dipole. And we know from our class this morning in particular, we sort of really tried to hammer the point home, all of these interactions have to do with dipoles, all of them. Whether or not you have a dipole interacting with an ion, with a permanent charge, whether you have a strong dipole interacting with another strong dipole through a hydrogen intermediate, which would be hydrogen bonding, or a permanent dipole interacting with another one, a permanent dipole forcing a nonpolar molecule to create a dipole. It's all dipoles. So the first site will be a sort of a good reminder as to what the hell a dipole is. Some of us don't remember, and how the molecular shape affects that. So we'll work with that for a little while. You'll create your own molecules and see how, changing the shapes, changing the electronegativities of the different atoms will affect that. And then we'll look at some real molecules, and you'll see you'll be able to determine the electronegativities of all the atoms. You'll be able to see the partial charges of all the different atoms due to the electronegativities, and then the individual bond dipoles, and then how that turns into a net dipole for the molecule when you add them all together. So we'll collect all that information, and then we'll go to the second site, which looks at the states of matter. And what we're going to do there is take the lessons we learned from the first site, figuring out which molecules are polar, which are nonpolar, which have stronger polarities, which have weaker, which can form hydrogen bonds, which ones can't, and use that information to predict what the boiling points of these different molecules are going to be. And you're actually going to measure the boiling point of each one of like four molecules we're going to look at. I'm not going to tell you how to do that, but hopefully you'll figure that out for yourself. So we know that the three main intermolecular forces: dispersion forces, dipole-dipole interactions, and hydrogen bonding, the main ones. We're not really going to be dealing with ion interactions today, although there's a question about it in the lab. Hopefully you'll give that a little bit of thought. So this is the screen that'll pull up when we go to the first site, and then you'll download applet, and hopefully, fingers crossed, it'll run. I don't know if your computers will have a problem with Java or not. I think there's two different ways they can run. They can either run through HTML, HTML5. Believe me, you guys hopefully know more about computers than I do. So they'll either run through that or run through Java. I've had success. I'm running Windows 10 here, and I've had success running with Java. It seems to work pretty well. So we'll go to that site first, do some experiments with molecular polarity. Here's the first screen. And so we can look at 2 atom molecules, then we'll look at 3 atom molecules. You can see you can vary the electronegativities here and see what effects it has on the polarity of the molecule. And you could even set up an electric field. See these 2 plates. You can say have an electric field and see how that interacts. Natalie, yes, question.
It says this type of file can harm your computer. Should I be worried?
No, shouldn't. No, it may, but it won't. Yeah, I mean, you can trust these. I mean, it was written by the University of Colorado. They're not in the business of downloading viruses to everybody's computer. So
I will download.
It's just an automatic response that you'll get because it's going to be downloading an application. So anytime you download an application, it's going to ask you that.
Okay.
Yeah. So yeah, so people, yeah, why don't we just do that? We'll just go to the site and see if that works.
Mine said it can't be downloaded.
Okay. Can't be downloaded.
It says it can't be opened because it's either not supported or it's been damaged.
Okay. Kind of figured this was going to happen. All right.
Yeah, I had the same problem.
Not be opened because it's from an unidentified developer.
Yeah, I can download it, but I cannot use it.
Okay. Here's another. You can go to this particular site. Can everyone see this one? Just highlight it.
Can you copy it into the
I'll see if I can put it on whiteboard.
So I was able to download and use it. So should I just switch over to the other one now too?
No, if you can use it, that's awesome. So you've got Java, I'm assuming then?
Yeah.
Yeah, I kind of figured everybody did, but maybe not. You share.
I mean, yeah, I think just yeah, because I just updated my Java. That's why.
Yeah. So here's the
HTML version of it.
Yeah. So here's the site to go to. So can you copy from this?
I don't think
You would need to like. Can you copy that link and put it in the chat of this Zoom meeting, and then we could go on it.
Okay, that's a great idea. Okay, let me do that. Here we go. There it is.
Yeah, there you go.
Okay. Yes, that should take you to this site. So this was a site about intermolecular forces and molecules. And it has different links. If you go down a little bit under the simulations, it has molecular polarity HTML5. You could try that one. Maybe that will work better for you. See what I get when I go there.
I just downloaded the HTML5 version. If you go on the link that you have,
that works better.
Yeah, it didn't download it as a jar file, which it did in the beginning. If you go to the link, there should be a button on like the bottom right that says switch to HTML5 version. You just click that and then hit download. It should download it to your computer, and you should be able to open it because it'll save it as an HTML file, which will open in your browser.
Yeah, the HTML
Yeah, that would
or
work for me.
Okay, yeah, which either one, it doesn't matter to me. They should hopefully they should act the same. Although I think one has like real molecules and the other one doesn't, which is going to be a problem. But let me see if I can. Yeah, you can see that how we're sort of making this up as we go along. there's bound to be some hiccups. Why am I not getting? Probably because I have 14 tabs open. Probably isn't great. Yeah, it's not happening. Try it again. No, I'm not able to connect through that one. Well, I'm going to pull up the. Oops, I'm going to. Yeah, so this is the molecular polarity screen that I have. So do people have the real molecules one tab on theirs?
Yeah.
Yeah.
Oh, you do? Oh, that's great. Okay, good.
Yeah.
Because I was worried the HTML version didn't have it. So good. Okay. All right. So since
Okay,
Oh,
wait,
wait.
mine didn't work.
This is real. Never mind. This is real molecules. Is not available in the HTML5 version.
Damn it. I knew it.
Right. Then why have the tab? That's just misleading.
Oh, so the tab is there, but it doesn't work.
Yeah, it just has to go download the Java version.
And for some reason, you can't do that.
Yeah.
Okay.
Do we get an A for effort?
Well, we can do the first. We can do the first part of it, and actually, we could possibly still do it with their 3-atom set. Let's just try it anyway. So let's just go to 2 atoms first. Let's give you an idea. So here we've got your basic diatomic molecule, and it's sort of set, as we can see, with difference in electronegativity between them. So when we click on view dipole, there's nothing there. And if we click on partial charges, nothing as well. And if you look at the electron density or the electrostatic potential, there's no difference. It's all the same all the way around. But if we change the electronegativity, let's say we give atom A high electronegativity and atom B a very low electronegativity, watch what happens. You can see what happens. We get the dipole becomes really big. So can anyone tell me what the difference between the bond dipole and the molecular dipole would be for this molecule? What's going to be the difference between them? Man, everyone's really quiet. What do you think?
Shouldn't it be neutral?
So you think for the molecule, it'll be there won't be any dipole for the molecule?
Yeah, because it evens out.
How does it what evens out?
Well, I see that on one side it is very positive, on one side it's really negative. So
Mhm.
when it's combining, it's having
What's-
a very
What's combining though? I don't understand what's combining. What do you mean by that?
like when the two atoms are bonding to make a molecule.
Mm-hmm.
The
I think what he meant is that when one is when both atoms bond together, so
Mm-hmm.
the whole molecule doesn't have electronegativity because it's the net electronegativity is 0. Is that what you mean?
Yes.
It's not going to be 0, though. I mean, this bond dipole that we're looking at, let me get my annotations to work. This that we're looking at right here, that's the dipole form in that bond between atom A and atom B. So since atom A is a much higher electronegativity, it's pulling those electrons that it's sharing with atom B toward itself. And so this is going to, A is going to stay partially negative, and B is going to stay partially positive. That's not going away. So my question is basically, if this is the bond dipole here, what's the dipole going to be for the if that's the dipole for that bond, what's the dipole going to look like for the whole molecule?
The same direction?
Same direction. Mm-hmm. Will it be the same size? So the overall dipole, you're saying, will point in the same direction, but will it be the same size? What do you think? So the overall bond, that's just the bond dipole there. So the overall molecular dipole will also point in this direction. But will it be the same size? Will it be just as big as the bond dipole is? Would we expect the size of it to be the same?
Yes. It could be.
Yes, exactly. Because there's only one bond in this molecule. And the molecular dipole is basically a sum of all of the bond dipoles in that molecule. And there's only one. So the bond dipole and the molecular dipole are the same because we add all the bond dipoles up to get a net dipole for the molecule. And since there's only one, we add that one up, it's going to be the same. So basically what we've got here is this would basically look like what HF would look like. So HF would look like this because, or sorry, the other way around. No, that's right. Yeah, so atom B would be the hydrogen with the low electronegativity. Atom A would be fluorine with the high electronegativity. And so this would have the partial negative charge and this would have partial positive charge. So this tells us, so that this partial negative charge tells us that this end is going to interact with another molecule that has a partial positive charge. So if it's another HF, it'll interact like this. And here's my positive, here's my negative, and then the interaction is going to be there. Whereas the positive end is going to interact with another fluorine, or with a different molecule altogether if it's a mixture. So what happens if I turn an electronic field on? Oh, wait a minute, mouse back. It will align itself. Let me unclear the drawings. it will align itself with the electric field. Let me switch them around. You see that in an electric field, the partially positive side is going to align itself with the negative charge because positive and negative interact, and the partially negative side is going to interact with the positive pole over here. Oh, man. Yes. So here I've got my cathode. Here I've got my anode. So these two are going to interact, and these two are going to interact. And how much they interact depends on what the difference is here. So you can look at the electron density. You can see that there's more electrons closer to the B. That makes sense because it's more electronegative. It's pulling more of those electrons toward it. And what the electrostatic potential means is how charged is it? That's all that means. So electrostatic means, is it positively charged or is it negatively charged? That's all that means. So wherever the electron density is greater, it's going to be the negatively charged. It's going to be the negatively charged part. And wherever the electron density is less, that's going to be our positively charged part. Okay? So let's go to the 3 atoms. Because now you can see that the shape is going to be important. So let's make water, for instance. So which atom would be oxygen here if this was water?
E.
Right. So we would give that a high electronegativity. And A and C would be the hydrogens, right? So we'll give those low electronegativity. So let's look at the bond dipoles. So you see that the bond dipoles are oriented along the bond because, you know, they're the dipole between those 2 atoms. So we can see over here that between the oxygen and the hydrogens, the dipole is going to be pointing toward the oxygen because it has a partial negative charge, right? Because it's pulling, it's basically, and it's going to be even more partially, have a higher partial negative charge, because it's pulling this pair of electrons from this hydrogen, and it's also pulling on that pair of electrons. So it's pulling on 2 pairs of electrons, so 4 electrons in total it's pulling on. So the charge of this oxygen is going to be a little bit higher than if it just had a single hydrogen bound to it, okay? So this makes this that's why water is so polar, because oxygen is basically pulling on both those bonds. So each of those bonds, each of those dipoles is pointing towards oxygen, but at an angle, right? So what would be the overall bond dipole when we look at the, I'm sorry, what would be the overall molecular dipole? Let me clear.
Straight upward.
Yeah, it's going to be straight up. And it's going to be slightly larger than either one, but not quite as large as both of them added together because they're at an angle, right? And look what happens when we change the angle. If I make this angle even more, this dipole gets even bigger. Because now both of those bond dipoles are pointing more and more and more in the same direction. And so my molecular dipole gets bigger and bigger and bigger. But what if this was a linear molecule? What would happen if this was a linear molecule? I'll just take the molecular dipole.
Its dipole is 0, like none.
go away.
Yeah, it'd be 0, right? Because basically we're adding two equal forces in exactly the opposite direction. And so when you remember, a force has both an amount and a direction. Like when you'll learn in physics, these things are called vectors, right? And vectors have an amount, and importantly, they have a distance or a direction. And so you can't just add two velocities together and have them, because if they're going in opposite directions, they basically cancel each other out. So here we can see this little thing. I don't even know if you can see it down there. This tiny little dipole down there at the bottom. Now it's gone. Now it starts. You see how it starts? Depending on the direction. If it's absolutely linear, you get nothing. Yeah, so here it's absolutely linear and you get no dipole. So this would go from having, so in this instance, water would have no polarity. If it was a linear molecule, water would be nonpolar, and none of us would be here to talk about it. But it isn't. It is bent. And so it has this overall dipole to it. And we can also look at the partial charges. And so you can see that the partial charge on the oxygen is going to be basically twice as much as the positive charges on the two hydrogens, since it's pulling electrons away from both of them, okay? And let's turn the electric field on. And you see that it will always polar molecules will always orient themselves so that their overall molecular dipole, the negative part, will orient itself towards the positive plate, and the positive part will orient itself to the negative plate. That's basically the easiest way to see if a molecule is polar, is to put it in an electric field and turn it on. And and you can actually look and see if the molecules orient themselves. And if they do, it has some polarity. And so you can mess around with different electronegativities here. The problem is, you won't be able to do the real molecules. Basically, what I can do is I can go through the real molecules, and then you can write down the table. Okay, does that sound fair? Because basically, I wanted you to fill out this table when you looked at the real molecules tab. We were going to look at 6 different molecules. We're going to put in what atoms are in there, what the electronegativities of each atom is, what the partial charge on each atom is. Are there bond dipoles? Yes or no? Is it a polar molecule? Yes or no? And then basically, what are the IMFs? What are the intermolecular forces involved?
Atoms, you mean how many atoms?
No, just which ones. Like,
Okay.
it has nitrogen, hydrogen. This one,
Okay.
carbon, because some of them have 3 different ones, some of them have 2 different ones. So we could go through that, since a lot of you don't have, or for some reason you can't get the Java to work. I can go through it here, and then you can write down the numbers to do that. Does that sound fair?
Yeah.
I mean, it looks like
It's the only thing we can really do. So.
Right, and then the other part, you will be able to do on your own. So, I'll have to find out some way to get this to work without Java, because this is important. Anyway, let's go to the real molecules. So you guys can play around with this and see how the polarity is involved with not only the shape, or not only the dipoles involved. Oh, look at it. It's orienting itself very slowly. That it's the dipoles in the bonds that determines whether it's you can have polar bonds in a non-polar molecule, just based on what the shape of the molecule is. So when we go to real molecules, first one I'll do is ammonia. Where is ammonia? Here we go. So we've got two different atoms. We've got nitrogen and we've got hydrogen. Okay, so those are atoms that we're involved with. So we want to know, let's look at the electronegativities. So we want to see the electronegativities will tell us whether or not the bonds themselves are polar, right? So the atom electronegativities. So the nitrogen has an electronegativity of 3, and hydrogen has an electronegativity of 2.1. So is that going to give us polar bonds or non-polar bonds?
Polar.
Polar, right? It's more than like 0.4, 0.5. It's like 0.9 difference. So that's going to give us polar bonds. So when we look at the bond dipoles, we should see, what direction are they going to be pointing in? They're going to be pointing toward the nitrogen or away from the nitrogen?
Toward the nitrogen?
Mm-hmm. Toward, right? Because dipole always points toward the negative, the more negatively charged atom, and away from the more positively charged atom. That's why we have this sort of little positive part here. So let's do that. Click on the dipoles. Mouse. So you can see it's a little bit of a mess. We got 3 different dipoles, but they're all pointing along the bonds, so that we have the bond angles. Oh, by the way, what would the bond angles be here? What do you think? See if anyone could remember that from old Vesper.
120?
120. Why do you think 120? What's the shape anyway? What's the shape of this molecule?
Tetrahedral. Oh no.
Yeah, trigonal pyramidal. I think somebody had it there.
I tried.
In other words, remember that there is a pair. There's a pair of electrons here. Remember? So nitrogen has a lone pair. So what do you think the bond angle is going to be here between them? Is it going to be, remember, with a perfect tetrahedron, it's like 109.7, I think, for a perfect tetrahedral shape. So are these going to be, this angle is going to be more than that or less than that?
More than that.
I got more.
What?
I got less. What do you think?
Exactly the same.
Or exactly, I got it exactly the same. Somebody had to say it, right? Or exactly the same. Let me see. So you remember that lone pairs actually repel the other atoms away slightly. And so if I look at this angle, it's going to be slightly more than 109. And these angles are going to be slightly less than 109. Yeah, okay. So here's my 3 bond dipoles, all pointing along the 3 different bonds. So you see they're sort of pointing in 3 different directions. What's the overall molecular dipole going to look like? what direction is it going to be pointed in?
Toward the nitrogen.
Is it going to be pointing up or pointing down? And then what direction? It may be pointing in a different direction.
Pointing in the lone pair direction.
Which direction?
Upward.
Upward.
Up, straight up?
Yeah.
Okay, so like this?
Yeah.
Okay, let's see. It's tricky going back and forth. Yes, exactly. So, yeah, so the overall dipole is pointing up because the nitrogen is slight positive charge or slight negative charge on it, and the 3 hydrogens have a slight positive charge. And so the net molecular dipole is straight up toward the nitrogen and away from the hydrogens. So this will give you an idea. I think I asked for the partial charges. Oh, hang on. Home deliveries. Yeah, so these are the partial charges. And you can see, like, sort of basically like relating to what we were talking about this morning, that the more electrons that a really electronegative atom has access to, the more it can pull on, the more its partial charge is going to be. So like nitrogen, when it was in a triple bond with carbon, had 6 electrons it could pull on. And so it could have a really strong partial charge. In fact, you can see that the partial negative charge on nitrogen is like it's slightly more than 1. So it has the same amount of charge on it as an ion. So that's why ammonia is so polar. It's even more polar than water, because it has this full charge on it. Oh, you move it around. Ooh, sweet. Yeah, so nitrogen has a partial charge of -1, and the 3 partial positive charges on the hydrogens are all 0.34. You can see that they basically add up to 0, right? Because since the whole molecule has no charge, the charges, the whole partial positive and partial negative charges should equal 0, right? Okay, so everyone's got the partial charges, and then you can see. Let me just flip this to one side. You can see this a little bit better. Oh.
So the partial charges are the negative 1.01 and 0.34?
Well, there's 3 that are 0.34, right? We have 3 different hydrogen atoms. So you add up all the positive charges, partial positive charges, and all the partial negative charges, and they should equal 0.
Oh, okay. Because this is on the
This
chart.
is a neutral molecule. This is not an ion. Even though the partial charge in the nitrogen is so great that it basically acts like an ion. So it's much attracting power to pull positive charges to it as a negative ion would. That's how electronegative it is.
Okay. I was just asking because of the table says there's partial charges for 3 atoms. So I was just like, do we fill out all 3?
Oh, yeah, it's for each one. So yeah, so partial charge in atom 1 is 0.334, and the atom 2, whatever it is -1. Yeah, there's only 2 different types of atoms.
Okay, so we
4 atoms total. Yeah.
Blank.
Yeah,
The third one.
Yeah, because there's only 2.
Okay.
Yeah. So when we look at the electron density, you see there's a big difference from one side to the other. And you can see it even greater when we look at the electrostatic potential. you can see that the negative side is highly negative and the positive side is highly positive. So this is basically as polar as it gets. This is a really polar molecule. So think about what kind of intermolecular forces would be involved in holding ammonia atoms or ammonia molecules together. What is possible when you put that in the last bit of the table. So let's look at CH3F. CH3F. Or fluoromethane. So I think it's fairly obvious to see which one is the fluorine, right? Usually when we do these ball and stick diagrams, we do halogens in green so they sort of stand out. So fluorine is on one side of it. So when I look at our bond dipoles, you can see that let's see if I move this around, it will help a little bit. So we've got three basically pointing toward the carbon. Actually pointing toward the hydrogens. Anyone have an idea of why that would be? Why in this instance the hydrogens would be slightly more negative than the carbon? That's not what we would expect, right? Oh, actually, no, sorry, it's the other way around. They're slightly pointing toward the carbon. That first makes more sense. But what is it that's pointing them toward? Why are they all pointing toward the carbon? Because there's not really that much of a difference between the electronegativity of carbon and hydrogen. That's not really a polar bond, but now they look polar. Why would that be?
Because of partial charges.
Mm-hmm. Let's look at the partial charges. Here we go. Maybe you see it this way. Now we look at this time, we see that the carbon has a slightly negative charge, which is strange, right? You wouldn't expect that. Why does it have a slightly negative charge here? What do you think is responsible for that? I'll give you a hint. Let's look at methane. Let's go back. I'll go back to fluoromethane. So, why do you think you would expect in this instance that fluorine is a lot more electronegative than carbon, and that fluorine should have more of a partial negative charge than carbon does, but it doesn't. Why do you think that is?
Is it because like all the hydrogens are pointing toward carbon and carbon is pointing toward the fluorine?
Mm-hmm. Yeah, basically it's because the fluorine is basically pulling a electrons away from carbon, right? Fluorine is pulling electrons away from carbon, and so it's slightly negative. But the carbon, fluorine only has 2 electrons on which to draw. It only has that pair of electrons that it can pull on from the carbon. So it only has access to 2. Carbon has access to 6 electrons. It can pull on the pair of electrons for each of those 3 hydrogens. So there's 2 from hydrogen 1, 2 from hydrogen 2, and 2 more from hydrogen 3. So it has 6 electrons to pull on. So since the fluorine is basically pulling on the electrons from carbon, carbon then pulls on the electrons from hydrogen. And so you'll actually see that the carbon is slightly more negatively charged than the fluorine, which you really wouldn't expect to see. But because, excuse me, it's because the carbon has more electrons to pull on. So it doesn't pull on them as much as the fluorine does. The fluorine is much more electronegative, but it only has 2 electrons to draw on. Carbon has 6. So even though it doesn't pull on those 6 electrons as much as fluorine would, it can pull on them enough so that its partial negative charge is even higher than fluorine. Okay, so there's your, so there's bond, they're the bond dipoles.
The assignment of actually the experiment and see what else we can say.
Is that a question, or is that was that a question? Is that Janelle?
No, that was from Matthew.
Oh, okay.
Probably someone talking to him.
Yeah, sorry about that.
Oh, no problem. I thought you had a question.
No.
Yeah, so you can take down with so there are bond dipoles, but strangely, the dipole between the fluorine and the carbon actually points toward the carbon, which is odd. You would not expect that. I mean, you can see it here. It's really small. It's really weak, but it's there. So when we look at the overall dipole, the overall dipole points straight up through the fluorine because the 3 bond dipoles are basically all pointing toward the carbon. And then when you add them together, just like the water, we had 2 dipoles pointing toward the oxygen, and when you added them together, they pointed straight up. Same thing is true here. So we do have bond dipoles and molecular dipoles. It's a polar molecule. And this is what the overall electrostatic potential would be. So it's slightly more negative on the top and slightly more positive on the bottom. So it's not as polar as one would expect it to be, just based on the fact that carbon has a higher negative charge than you would, or slightly more partial negative charge than you would expect it to. So then ask yourself, what sort of interactions, intermolecular forces could this molecule engage in? So do you figure that this would boil at a lower temperature or a higher temperature than ammonia, the last one we looked at? What do you think? Would this have more intermolecular forces than ammonia or less?
More?
More? So you think it would boil at a higher temperature than ammonia?
Does this have to do with the molar mass?
Nope.
Okay,
Well,
never
it
mind.
does. I mean, if there's a big difference in molar mass, then you would expect one would have more dispersion forces than the other. But in this instance, there's not much difference between them.
Oh.
It's a slightly larger molecule than ammonia, but not by a whole lot. So I want you to think about, what forces it would have that would be greater than ammonia and which forces would be less. Okay, think about that and then put that in the last column. All right. So shall we go to the next one? Does everyone get all the information they needed from this one? The partial. The negativities. Needed the negativities.
I have a question.
Yes.
What's the last column for IMF possible?
Yeah. What are the intermolecular forces possible?
Oh, okay. So like, do I just need to write like the names of it?
Yeah. So you just put down like dispersion, dipole, hydrogen bond.
Is this one hydrogen bonding?
What do you think? Got a fluorine.
I think so.
Can it hydrogen bond? What are the two? Remember, to make a hydrogen bond, you need two things. You need a hydrogen bond donor, and you need a hydrogen bond acceptor. So the donor or the acceptor is like is basically a free. Just want to draw. So the acceptor is going to be like a free fluorine, or fluorine bound to something else, an oxygen bound to something else, or a nitrogen bound to something else. Do we have that here?
We have a fluorine.
Yeah, so we do. So we have a hydrogen bond acceptor. Have that. We have fluorine bound to something else. So far so good. We also need a hydrogen bond donor, which is we need hydrogen bound to either fluorine so we need a hydrogen bound to either nitrogen or fluorine or oxygen. Do we have that here?
Yep.
Mm-hmm.
Do we?
No, we don't.
Oh, we
Oh, wait.
don't.
It's not bounded to the.
No, we don't. We don't have that. Yeah, the hydrogens are all bound to carbon.
Oh.
So if the hydrogens are bound to carbon, that means they're not going to be nearly as have nearly as the high a partial positive charge as if they would have if they were bound to nitrogen or fluorine or oxygen directly. Because if those hydrogens are bound to fluorine directly, they're much more positively charged. So that difference because you remember with the partial charge on the ammonia, I think they're like 0.34, and the partial charges on them now, if I can get my mouse working, the partial charges on them now is
0.13.
0.13. Big difference. It's more than twice as much. And so they're not nearly going to have the same potential for forming hydrogen bonds if their partial positive charge is so low. Because when they're bound to either nitrogen directly, fluorine directly, or oxygen directly, their partial positive charge goes way up. And here, they're hardly positive at all. So this fluorine could accept a hydrogen bond, but it can't generate one. It can't donate one. So it can't hydrogen bond with itself. It could hydrogen bond with water. If it had, if water was there, it could. So if I had a water here, there might be a hydrogen bond between the fluorine and this hydrogen. But even then, it's not going to be as strong because you can see that the partial negative charge in the fluorine isn't all that great either. So it probably, if it did hydrogen bond, it'd be pretty weak. Okay?
Mm-hmm.
Yeah, so this can't form hydrogen bonds by itself. So we can't put hydrogen bonds as potential. So so that leaves us with only two. There's only two potential ones left. It can have dispersion forces And remember, they all can have dispersion forces. Anything can have dispersion forces. So dispersion forces better be there for every single one. That part's easy, right? But, so we know it can do that. But can it do dipole-dipole interaction? Is that possible? So if I have two fluoromethane molecules together, can they interact in a dipole-dipole orientation? If I draw it like this, maybe it'll be a little easier to see. Now, can that molecule have a dipole-dipole interaction with another fluoromethane molecule? What do you think?
What are the conditions for dipole-dipole again?
Got to have a dipole, and it does. And you have to have one end is slightly negative, one end is slightly positive. So the slightly positive end of one molecule interacts with the slightly negative end of another one. Basically, they will interact. So here we have, on this molecule, we have a slightly negative side and we have a slightly positive side. So is a dipole-dipole interaction possible?
Yes.
Yes.
Yes, by definition, right? If I have a slightly positive side and a slightly negative side, I got me a dipole, permanent dipole. And it may not be the strongest dipole in the world, but it is one. And so we will have a dipole-dipole interaction, but just not a particularly strong one, because the slightly positive side isn't all that slightly positive, and the slightly negative side isn't all that slightly negative. So this is going to be weak. So fluoromethane is going to have a slightly higher boiling point than just plain old methane, but not by a whole hell of a lot. And we can probably look that up. In fact, I probably should have put that in one of the
Post-lab questions?
well, none of the post-lab questions, just one of the columns.
Oh.
Yeah, look up the boiling point, because I'm curious now of how much different it is from methane. It's gonna be slightly higher, but I don't know how much higher it would be.
I can look it up.
Oh, there you go. All right, so let's go to the next one. So if we replace all of the hydrogens with fluorine, what does that get us? All right, so I'm going to change all the hydrogens to fluorines now. So tetrafluoromethane. So all four are methanes. So where am I, is this going to have bond dipoles?
Yes.
So it's got 4 bonds. Are they polar bonds or non-polar bonds? Let's look at the electronegativity. So you can see carbon's got an electronegativity of 2.5. Fluorine's got an electronegativity of 4. So are those going to be polar bonds or non-polar bonds?
Non-polar.
But there's a big difference in electronegativity. There's a difference of like 1.5 in electronegativity. Doesn't that make for a polar bond?
I thought it was 1.0. Wait, what? 0.7?
Oh, it makes.
Isn't like
Oh, that's a pretty big difference.
That's a big difference. Yeah, any difference more than like 0.5 makes it polar.
Mm-hmm.
Yeah, so those are polar covalent bonds, all 4 of them.
Oh, I found the boiling point differences.
Oh, okay. What was it?
Methane is negative 161.5 degrees Celsius.
Okay.
Methane is negative 78.4.
Oh, so a fairly big difference, but it's still really low. Okay.
Mm-hmm.
Minus 78. Okay, cool. Thank you.
Mm-hmm.
So here we got CH4, or CF4. So we already think we're going to have bond dipoles, right? Because those bonds are polar. There's a big difference in electronegativity between them. So the question is, which direction are they going to point? Are they going to point toward the carbon in the middle or toward the fluorines? Which direction are those arrows going to be?
Toward the carbon.
Towards carbon.
Towards carbon. Remember, they point towards the more
The less.
negative charge. Yeah, they're going to point toward the fluorine because the fluorine is a higher electronegativity. So it's going to be pulling electrons away from carbon and towards itself. Okay? So those bonds, so carbon is going to be partially positive charged and the fluorine is going to be partially negatively charged. Now, let's look at the partial charges. So each one of the fluorines has a small partial charge, like 0.11, hardly anything. And the carbon in the middle has a partial positive charge of 0.42. So you can see again, when we add them all together, you get zero because it's a molecule without a charge. So why do you think the fluorines have so little charge on them? Whereas we expect fluorine to have like when it's bound to something, to have a much higher partial negative charge. Why do you think they're so small with this molecule? Like the last time, actually the last one wasn't much either, but usually if we have like a fluorine bound to something, its net negative charge is higher. Here it's really small. Why do you think that is?
Is it because there's no hydrogen bonding?
No, not really. It has something to do with what else is bound to the carbon.
Other fluorines?
Yeah, I mean, basically, they're all pulling on the same thing. And so it's like you're having a tug of war. If you have a tug of war between two equal-sized sumo wrestlers, neither one of them is really going to make much, be able to move very much, right? And the same thing's true here. You've got basically 4 sumo wrestlers all pulling on carbon. And so none of them are going to get much from it because they're all pulling in opposite directions. So here we have dipoles pointing away from the carbon and toward the fluorines. What's going to be our molecular dipole? When we add them all together, what are we going to get? If we sort of move this around, it gives us a better idea. Yeah, I think you'd see them all well in that regard. So when we add all of those together, what are we going to get as far as a molecular dipole?
Is it 0? No.
Yeah, nothing.
Oh.
When I click, see nothing appears because there is no molecular dipole because we have 4 dipoles pointing in exactly opposite directions. Now this is a perfect pyramid, so they'd all be the 109.5 degrees, pointing opposite from each other. So when you add them all together, you get 0. And when you look at the electrostatic potential, or the electrostatic potential here, you can see there's not much difference. It's basically equal all the way around because we're looking at the external atoms. We can't really look at the carbon because it's in the middle. We're looking at the surface of the molecule, and the carbon isn't on the surface. It's the fluorines that are on the surface, and they all have the same charge. So the potential, the difference from one side to the other is 0. So this is a non-polar molecule. It's got 4 polar bonds, but since they're all pointing in opposite directions, when you add them all up, you get 0 as far as polarity goes. So think about what kind of intermolecular forces this can make. And I'm thinking the boiling point of this is going to be less than for someone, whoever looked it up last time. For C4F, it's going to, I bet it's going to be greater than CH3, but less than CH3F. And why do you think that would be? Why do you think this would boil at a higher temperature than just CH4? CH4 is equally nonpolar, but this would boil at a higher temperature. Why do you think that would be? Have you looked it up? Do we know what it is?
No. Bond strength?
No, the boiling point for C.
Oh, the boiling. Got you. Okay. For CF4, it's negative 127.8. And you want CF3?
No, that's fine. That's, yeah, so basically, yeah, it's just what I thought. So it boils at a higher temperature than CF4, but it boils at a lower temperature than CH3F. So what do you think is the difference? Why does it boil at a higher temperature than methane alone? It's just as nonpolar as methane, but it boils at a higher temperature, meaning the interactions between CF4 are stronger than CH4. What do you think those interactions are? Anybody got an answer? What do you think? Well, think about what kind of interactions can they do? What kind of interactions can CF4 actually pull off?
London dispersion.
It can do London dispersion. Can it do dipole-dipole?
Get it? I don't know.
No?
Oh yeah.
No, and oh yeah.
That's just what I think.
Which one is it? Is it no or oh yeah?
I think no.
It can't be.
I say no.
No, because there's no molecular dipole, right? You have to have a molecular dipole in order for that to happen. So it can't, and it obviously can't hydrogen bond because it's not polar, and there's no hydrogens here, so it can't do that. So the only force it has is dispersion force. But so the question is, why does it boil at a higher temperature than methane? Methane can only do dispersion forces too. But why does CF4 have a higher boiling point?
Size.
Exactly. Yeah, CF4 just has more electrons. It's bigger, it has more electrons. And the more electrons you have, the easier it is to force a little bit of a dipole. You can force these really small dipoles to form. And so CF4 is bigger, has more electrons. We say it's more easily polarizable because there's just more electrons. And anytime you can just tweak just one electron a little bit, you get that little bit of interaction. So if you have more and more and more electrons, you have more and more and more chance to make these interactions. So that's CF4. So let's look at water. We sort of looked at water already. We should probably know how this is going to go down. Water. Wait a minute, where's water? Oh, there it is. All right, there's my water. So I got my oxygen in the middle. So where is it going to have, let's look at the electronegativities. So oxygen 3.5, hydrogen 2.1. So if I got polar bonds or non-polar bonds. Now remember, we're only looking at
Polar.
Polar.
right.
Polar.
Telepolar, because we're looking at the difference in electronegativity between the two atoms involved in the bonds. And we have two bonds, and they're exactly the same. We have two oxygen-hydrogen bonds. And they both have a difference of 1.4 in electronegativity. That's big. That's a big difference. So these are going to be polar bonds. What direction is the arrow going to be pointing in for my bond dipole?
At each other?
Towards H.
Towards, they're either going to be pointing towards the hydrogens or they're going to be pointing towards the oxygens. Which direction they could be pointing in?
Toward hydrogen.
Hydrogen.
Hydrogen. I got hydrogen. Anybody else?
Oxygen.
Yeah, remember they point toward, point toward the more electronegative. Yes. Because they got that little positive part on them. Let me draw that out. They've got the little, when we draw a dipole, we draw it pointing toward the more electronegative, and when we put this little cross in it, it sort of shows us which side is more positive. So this little cross, or the positive, should be pointed toward the less electronegative, or the one that's going to have the partial positive charge. So we always point toward the more electronegative. So it'd be pointing toward the oxygen. So am I going to have, let's look at the partial charges. We need to put that in there. What do you expect? Do you expect the oxygen to have a high partial negative charge or not quite so high? Will it be close to 1 or closer to 1 or closer to a half?
Further away from 0?
Well, it's going to be away from 0. We know that because it's going to be a partial negative charge. But it's going to be like -0.5 or almost -1 like ammonia was.
Almost -1.
Why do you say that?
Because it has 2 hydrogen atoms, which is
that's
around 0.6.
That sounds logical. Yeah, it just sounds logical because it's pulling on 4 electrons. Now, last time when we looked at ammonia, that nitrogen is pulling on 6 electrons. This oxygen's only pulling on 4. So, but I would expect that the partial negative charge will probably be closer to 1 than it is to 0.5. Let's see. Yeah, it's right in between, basically. Yeah, it's -3/4. So it's more than 0.5, but less than 1. And we would expect that because it's pulling on not just a pair of electrons, but 2 pair of electrons. And so our partial negative charge in oxygen is like -0.75, and on the 2 hydrogens plus 0.38. And again, they should add to 0. So, next question. I'm going to have a molecular dipole, yes or no? And in what direction is it going to be pointing?
No, they cancel out.
Okay. So basically 0 then. Okay.
Yeah.
All right. Anybody else? What happens when you add these 2 dipoles together?
Because they have an angle, so they can cancel out, right?
Do you say they are or they aren't going to cancel out?
Not
They aren't because it's water. The molecular dipole will points upward.
So you're saying they are going to cancel or they are not going to cancel?
They are not.
They are not. Okay. Anybody agree? Well, I know some of you disagree.
They're not gonna cancel out.
They're not going to cancel. So I got 2 to 1. What do you think? Well, just think to yourself, is water polar or not?
Water is polar.
That you should know right off the top of your head. And so if it's polar, They can't cancel each other out. You have to have a molecular dipole in a polar molecule. That's the meaning of polarity, is that it has a molecular dipole. And since these are both pointing in generally the same direction, not exactly, obviously. If they're pointing in exactly the same direction, you just add them together, we get like a super big dipole. And if they were pointing completely opposite directions, they would cancel out. But since they're either pointing the same direction, slightly the same direction up, or in the same direction down, we add them together. But they're not going to be they're not going to be the twice as much. Let's look at the molecular dipole. What happens? What direction is it point anyway? Up or down? Up, right. It's going to point up, but you can see, so the direction, we add them together, it goes up, but you can see that the magnitude of it is not going to be twice those bond dipoles. It's going to be a little more than either one of them, but not as much as 2 times. It's not going to be 2 times because they do cancel each other out slightly by kind of pointing in a similar direction, but not exactly. So they point at each other a little bit, but not completely. And so our net dipole is up. So is this polar molecule or not? You know, I'm looking at a big ass molecular dipole there. So what does that tell us?
Polar.
Yeah, it means polar. That's what it means. Remember, that's the definition of polarity. If it has a molecular dipole, when we add all the bond dipoles together and something comes out of it, pointing in any direction, it's a polar molecule. Even if the dipole is really, really small, we say it's a polar molecule. We say it's not that polar, but it's still polar. All right, so we have 2 more to do. We have cyanide, hydrogen cyanide, and oxygen. So let's look at hydrogen cyanide.
Oh wait, sorry if someone asked this already, but what do
Sure.
you under atoms? Just add the atoms?
Excuse me?
Oh, what do we write under the atoms column? Do we just write nitrogen?
Oh, just write what atoms are in it.
Oh, okay.
Yeah.
Oh, it was that simple. Okay.
Yeah. Don't make it more difficult than it needs to be.
Okay.
And if it only has like 2 atoms, but leave the third space blank.
Mm-hmm.
Oh, okay.
Yep. So then you want the electronegativities and the partial charges. And then whether or not it has molecular dipoles, yes or no, bond dipoles, yes or no, and then whether it's polar or not. And then finally, based on all of that, what kind of intermolecular interaction is going to have. So let's look at hydrogen cyanide. So we can see from hydrogen cyanide is linear. It has a triple bond between the carbon in the middle and the nitrogen on the end. So there's our electronegativities. So see, nitrogen is 3, carbon is 2.5, and hydrogen is 2.1. So it's basically 2, 2.5, 3. So we're going to have bond dipoles here. Do we have any differences in electronegativity?
No, because the
We have
difference
we have
below-
some difference, right? Even if it's a small difference, we'll have some difference. Let's just see anyway. Let's just see whether we have any bond dipoles. And you can see we do. I mean, they're not great. They're small, but we do see them. Let's see if there's some way to, it's kind of hard to see the, oh, here we go. Oh, wait a minute. It's tough to see that one. There we are. They didn't make this easy. Right, sort of interestingly here, yeah, sort of pointing toward the hydrogen and toward the nitrogen. We wouldn't expect that because, or is it pointing toward the carbon? I can't, man, these arrows are so small. I wish we could blow, maybe we can blow this up. No, we can't blow it up. Anyway, let's look at the partial charges. That'll tell us what's going on. Yeah, they don't make this easy. Let's look at the partial charges. That'll tell us what's going on. Okay, so partial charge. On the hydrogen is 0.23 positive. On the carbon, 0.05, so it's barely positive, basically neutral. And the nitrogen is negative 0.28, so it's slightly negative. Yeah, so we would see the carbon is a little more negatively charged than hydrogen is because hydrogen is positive. So you'd have a small dipole pointing toward the carbon away from the hydrogen. And on the nitrogen, the arrow will be pointing toward the nitrogen, so, and away from the carbon. So you can see that both bond dipoles are pointing in the same direction. They're both pointing toward the nitrogen. So what's our molecular dipole going to look like?
They're pointing in the same direction, right?
Mm-hmm. Mm-hmm.
So they're not canceling each other out. So it's some kind of number.
No, actually they'll add together.
Yeah.
You take two small numbers, you point them in the same direction, add them together, they'll be additive. So yeah, when we look at the molecular dipole, it's bigger than either one because both of the dipoles are pointing in the same direction, not opposite directions like we saw before, pointing in the same direction. So when we add them together, they add up along that line that this is a linear molecule. So they're both pointing along the axis of the molecule and in the same direction. So we just add them together. So it's actually greater than either one together. So do we have a polar molecule here or a non-polar molecule?
Polar.
It's polar. And we can tell, let's look at when we put in the electrostatic potential, again, we have a positive end. So here on the hydrogen side, we've got a positive side, and on the nitrogen side, we've got a negative side. So we've got polarity. We have got a dipole. We have got a polar molecule. So think about what kind of interactions this molecule can do.
Dipole.
Yep.
And London dispersion.
Why can't it do hydrogen bonds? It has a nitrogen and a hydrogen.
The hydrogen's not bonded to the nitrogen.
Yeah, that's it. It's not bound.
That's right.
It's not bound.
That's excellent. Yeah. So this nitrogen by itself can accept hydrogen bonds. It has a partial negative charge, so it can accept hydrogen if it's given to it, but not when it's given to it by a carbon, because this hydrogen here is not nearly positive enough for it to be a true hydrogen bond. So for it to be a true hydrogen bond, that partial positive charge on the hydrogen needs to be higher. And the partial negative charge on the nitrogen needs to be higher as well. So it can form dipole-dipole interactions, but not hydrogen bonds. Yeah, excellent. All right, so last one. So everyone got all the information they need? The dipoles, the
Yes.
activities, the partial charges. Everyone got that? Okay, let's do the last one. So the last one is oxygen. That is one of the molecules you'll be measuring the boiling point of. All right, oxygen. Good old O2. There we go. So oxygen, we remember, has a double bond between the two, right? So the double bond and two pair of electrons on both sides. So it has this two pairs for 4 electrons, and it shares another 2 on the top and another 2 on the bottom. Now remember, one of these is going to be a sigma bond, and the other is going to be a pi bond, right? If single bonds are all sigma, and pi bonds, the second bond is always pi. So it shares a pair of sigmas and a pair of pi's for a total of 8. So they each have 8 electrons, both very happy. So, first, what are my electronegativities? And 3.5. So both oxygens have electronegativity of 3.5. So, am I going to have any bond dipoles?
No.
I got a unsure no. I'll take that. Anybody have a more sure no or a sure yes?
No. No dipoles.
That's a sure no. That's right. Yeah. There won't be a bond dipole because both have exactly the same electronegativity. So they're both pulling on those electrons exactly the same. So when you look at the electrostatic potential, it's the same all the way around because they're equal. So we look at the bond dipoles, there aren't any. They're not pointing in one direction or the other direction. So the molecular dipole, is a molecular dipole possible?
No.
No.
Let's see. No. No, if you have no bond dipoles, you can't have a molecular dipole. You can have no molecular dipole. If you have a bunch of bond dipoles that all add together to 0, you can have no molecular dipole. That's fine. But if you have nothing to add up, like nothing plus nothing is nothing, right? So if there's no dipoles in any of the bonds, you can't have a molecular dipole. So what are the partial charges? What do we expect the partial charges to be?
0.
Yep, gotta be, right? Has to be 0 because each of these oxygens is sharing and exactly the same number of electrons as the other one and pulling on them exactly the same. So they can't have a charge. My question here, can you force oxygen to become a dipole? We talked about it this morning in class. What are the circumstances in which you could force oxygen to become a dipole?
There has to be a higher electronegativity atom.
Yeah, either it needs to come into contact with another with either another pair of oxygen atoms, another molecule, where you get really weak London dispersion forces, or you could comes into contact with a strong dipole and forces the electrons to move from one to another. But what we talked about this morning was if we had an ion present, like in hemoglobin, if it comes, since there's an iron in the middle of the hemoglobin molecule, when oxygen comes into the presence of a +2 charge on the iron, it forces electrons to move toward it, right? And so this oxygen will become slightly negative and this oxygen will become slightly positive because the ion, +2 ion, is pulling electrons toward it because it's positively charged. And so it forces a dipole to form. And it's this induced dipole, we call it, that's responsible for you being able to breathe. So oxygen better be able to form a dipole or we'd all, die. So it's kind of important. Right, so no bond dipoles, no molecular dipoles, no partial charges. So is this polar molecule?
Mm.
Is O2 polar?
No.
No. No.
O2 is nonpolar.
It's nonpolar. If there's no bond dipoles, it's nonpolar. And it's in the presence of iron, it's forced to become polar very slightly. But that is an induced dipole. And when it's released from iron, it becomes nonpolar again. It's only when it's in the presence of a strong charge or another dipole does it become polar. Okay, so spent a long time in this. This is something hopefully you could have, we'll figure out some way for you to be able to do it yourself. What I want to do before we go is go to the other we go back here to go to the second, the second simulation, the states of matter. Should I put this in the, everyone has this already, or should I put this in the chat as well? I might as well just put it in the chat just in case.
Mine's working fine though.
Yeah, this one should work because this one doesn't need Java. Just in case no one's got it. There it is.
It still says I have to download it as a jar
Yes.
file.
Yes, but it's not Java. Hopefully you should be able to get it.
I can. It's Java.
Yeah, that's
Yeah, it's the same thing.
Oh, damn. Okay.
I have the HTML5 version, but I feel like that one's also going to be
No, that'll work. No, I don't think it is. Let me go back. I will give you the link to the other one. States of matter, HTML5. So this should be this. I think this is the same.
Which one are we working on again?
Anyone you can. Well, actually, no, it's the same. That's the same link. Simulation. Oh, no. Oh, that one's legacy. Never mind. Same. Yeah, try the second one. If the first one won't work because it's Java, the second one should. You should get to this page, and then yeah, just hit download. It gives you a jar file. You open that, and then it should give you something that doesn't require Java. Don't worry if it says, this will destroy your computer or whatever. So let me know if someone's still getting it.
The second link worked for me.
Yeah, that's what I figured. Yeah. So everyone should have, when you open it, I think it goes to solid, liquid, gas first. Everyone should have like this one open. Is that what everyone has?
I only have states and phase changes.
I have states
That's-
of matter.
That's fine. You just need the phase changes is all you need.
Phase changes. Okay. I mean, I'm using the HTML5 version because
Mm-hmm. And does it
Yep.
have what are the 3 tabs in that one?
there's not
There are
really
only 2.
tabs. I wish I could just.
You just have phase changes. Does it look like this? What I've got on the screen?
No.
Yeah.
Yes. No.
Well, it's not yellow, it's
Gray.
gray and not all
Yeah.
weird looking like that. But
Do you also have the one on the little chart on the right?
I have
yeah.
part of the right. Oh yeah. Okay.
Okay, yeah. So hers and ours are the same. Rachel's and I are the same.
Okay.
But ours are different from yours then.
Basically, you just need a way to measure the temperature, the pressure, and change the heat up and down. That's all you need. Okay. And do you have neon, argon, oxygen, and water as your 4 molecules?
Yeah.
Okay, cool. Right. So what I'm going to do is show you neon, how to do that, and then you'll do the rest of them yourself. Okay. And then we'll call an end to this hellish exercise. So basically what I want to do, what this will help us do is measure the boiling point of each one of these molecules. So what I want you to do is click on neon and click on cool and bring it all the way down as low as you can. I think the lowest it goes to is 1K. Won't let you go to absolute 0.
I'm trying to drag
It
the.
won't let me go at all.
It just.
It won't. You can't cool it.
It just brings it back up to the middle.
Yeah, it
Okay.
just stays in the middle.
Mine's went to 0.
Have to do it.
Well, yeah, it will stay, but will it stay? You put it. You have to hold it. Yeah, you hold it on cool, and when you let go of it, it goes back to the middle. But it stays.
It's still 0 though.
Oh, okay, I get it. Okay, you have to.
Yeah, you have to hold on to it. The little ice cubes come up, and then it'll take you down to 1K, and then when you let go of it, it'll stay there. So can everyone?
Are we
do
going
that?
to 1K or 0?
1.
I don't think it'll go to 0.
1.
Mine doesn't go to 0. Does yours?
Mine just stops at 1.
Yes.
Oh wait.
Oh,
No.
nice.
I meant
Very
0.
nice. So you should see.
Mine still says 0K.
I finally got 0K as well. Nice. Okay. So notice.
But all my little dots are in the middle. They're not on the side like yours.
Okay.
I don't think that matters.
It doesn't matter where they are. The
I don't know
question
if
is
or not.
what's happening to them?
Nothing.
Nothing, right? They're not even vibrating, right? They're just completely stopped. So at absolute 0, everything stops. And have a look at the pressure. What's the pressure?
0.
0.
0. Why? Why is it 0?
Because it's cold. Is your color?
Because there isn't any air inside.
Because it's not vibrating.
Well, there isn't any air inside. There's neon inside.
It's being vacuumed.
Yeah, there's neon in that chamber, but why isn't there any gas pressure?
Because neon is not in gas state in this case.
Right, there's no gas molecules present. At 0 degrees, there are no gas molecules. There are no liquid molecules. There's just solid because there's no movement at all. There's no molecular movement. So even in a like a regular solid, there's going to be some movement of molecules, but here there's none. So there's no liquid, there's no gas, there's just solid. So what happens is if we increase the heat a little bit, notice that even at like 8K, the molecules are starting to move. So here, we would have what I'd call that a liquid, right? Because they're moving. If I increase the heat a little bit more, now you see them starting to to move around. So that's definitely a liquid now, right? Because it's moving. You see the molecules are moving from one side to the other. So that's still a liquid. But is it a gas?
No.
No, I wouldn't call it, because we'll look at the pressure.
Oh yeah.
There's no pressure, right? So if I increase the heat a little bit, now what's happening to the pressure?
It's
Slightly increasing.
Yeah, it's going up, right? Because I've got molecules in the gas phase. And you can see them. You can see them bouncing around. Once you have molecules hitting the side of the container, that's what causes pressure, right? We learned that when we did the gas laws. The molecules hitting each other, like they were in the liquid, when they come in contact with each other, does not cause pressure. When they hit the sides of the container, that's when it causes pressure. And so now they're able to do that. And so the pressure has gone up. How do we know we've reached boiling point? How are you going to measure the boiling point of this? How are you going to know you've come to the boiling point? I think I wrote up in the lab write-up. The hint was, what's the definition of the boiling point of a substance? That's what you need to remember. That's how you're going to know. So what's the definition? Anyone remember what the definition of the boiling point is? It's super quiet. All right. How can we tell? Oh, go ahead. Go ahead.
When the vapor pressure of a liquid equals the pressure surrounding the liquid and the liquid, I don't know.
No. Yeah, you're right.
I was gonna say when the temperature remains constant, but the state changes. I don't remember exactly.
Oh, okay. Yes, that's one part of it. If we were doing a heating curve, and we were adding heat, and we saw at some point the temperature stopped changing, then yes, that would be the boiling point. But it looks like we can't really draw a heating curve here. We can't really plot it out. So without being able to do that, what's another way we could figure out what the boiling point is? And you were really close. Remember it has to do with the pressure. What does the pressure have to be at the boiling point?
Standard.
What does that mean, standard?
I think the temperature have to be constant at that time because it goes through the vaporization process.
That would be nice, but it looks if we could make a heating curve, that'd be a good way to do it. But it looks like we can't do that here. We can only measure the temperature and the pressure. So if that's all we can do, how are we going to measure the boiling point?
So instead we apply rule like if temperature increase, pressure should be constant. So when we reverse engineer it, like if the temperature is constant, so as it goes toward the boiling point, that the pressure should be increasing.
Well, the pressure is going to be as I increase the heat, the pressure is going to go up and up and up It's just going to just keep going up. So that's always going to happen. If I keep adding heat, the pressure is going to go up and up and up and up and up. But how am I going to know when I'm at the boiling point? Cool it back down again. So at the boiling point, what is the pressure? That basically is the question I'm getting at.
Equal to the vapor pressure of a liquid.
So the vapor pressure of the liquid, right, is equal to what?
External pressure surrounding the liquid.
Yes, equal to the atmospheric pressure. There you go. So we have to assume that this is at atmospheric pressure, and so once the vapor pressure becomes 1 atmosphere, that's the boiling. And so what you're going to have to do, so you can see that it's changing all the time, because it's going up and down and up and down and up and down. So what you're going to have to do is sort of, it's never going to go to exactly 1 and then stop. So everyone's going to get slightly different numbers. But what I'd like you to do is just sort of see if you can get close to it. If it's going like past 1 and then below 1, past 1 and below 1, past 1 and below 1, that's going to be pretty close to the actual boiling point. You can see here, I'm like at around 0.4 and then down and then back up. So looks like I need to go up a little bit, maybe like by a degree or 2.
What number would we use? The one that's above 1 or the one that's like right about to be 1?
Well, what you want is like basically for it to fluctuate around 1. If it's fluctuating around 2, you've gone a little too high. But if it's like just above, well, notice I just increased the temperature from like 30 to 32. And now it's fluctuating between like 1 and 2. No, it's going a little bit below 1 and then a little bit above 1. So it looks like I'm really close here. So it looks like 32 is probably going to be as close as I'm going to be able to get. You can do 31, 30. But yeah, so it's going to be close, like 30, between like 30 and 33, somewhere around there. It's not going to be super, super precise. What you want is it to be fluctuating around 1. So then do argon and oxygen and water. And then, get you figure out what the boiling point is for each one. Look up what the actual boiling points are. See how close you got. And then basically, part of the lab is to explain why the boiling points are different from each other. Okay? Looks
From
like
the one
30,
that we measured and the one that we got?
looks like 31's right on the nose. It's see how it's going up? It's going up and down right around 1. But I think 31 is pretty much perfect.
So once the pressure hits to 1 and it fluctuates in between, that's when we assume that it's the boiling point?
Yeah, I mean, you're not going to get it exactly, but you'll be off by like 1 or 2 degrees. It looks like 31 is about as good as you're going to get. Because 30, it was going up and down, but it was above 1 sometimes, but spending most of its time below. And at 32 is spending most of its time above 1, but at 31, it looks like it's spending equal time above and below 1. So that's going to be close enough for me, I think.
Okay.
Yeah,
What about the part that says the EMF's responsible?
Yes. What are the the extra molecular forces available?
Okay.
For the differences. So you're going to see neon, argon, oxygen, and water all are going to be all different. And then
okay,
to you to figure out why that is. That's part of the lab. That's part of the write-up. Like, how come?
All right, got you.
Any questions before you go?
Oh, when does
Can
this
you
do?
repeat the EMF thing?
Oh, EMF. It's just the extra molecular forces. Intermolecular forces. It's IMF, isn't it? Not EMF? Did I put
You put EMF on the PDF.
Oh man,
Yeah, are we
Yeah.
hunting ghosts? Like, what's happening?
IMF, International Monetary Fund.
Professor,
No, it's
but-
in the intermolecular forces. EMF's like an old electronic dance band.
When does this do?
Week from today.
Okay.
Is this our last lab, or do we have another?
This is the last one. Yep.
Okay.
For this lab report, do we just like put the tables and that's it, or like?
No, you always have to have a title, a purpose, a procedure, data tables, and then your conclusions.
How about discussion? Do we need discussion?
Yeah, that's like basically answering the questions. This is
Oh, okay.
a discussion. Yeah. All right, everyone cool?
Clear.
Or as cool as you're gonna get?
So far,
All right.
yeah.
All right, thanks everybody.